This is Space Minds by Space News. In this week's episode of Space Minds, host David Ariosto speaks with Riley Duren, CEO of Carbon Mapper and veteran of NASA's Jet Propulsion Laboratory. Duren discusses how his nonprofit is harnessing cutting-edge satellite technology to track methane and carbon dioxide emissions, the super pollutants driving climate change.
Riley Duren, Chief Executive Officer at Carbon Mapper and a longtime veteran of NASA's Jet Propulsion Laboratory. It is so good to have you on the pod.
Thanks, David. It's great to be here.
Yeah. So I was really looking forward to this conversation because you kind of have this interesting nexus, the symbiosis between these NASA level systems of engineering and nonprofit climate advocacy. And so you kind of have this blend of this hard science and tech innovation and aspirations for real world impact. So I think that's probably a good place to start this. What is Carbon Mapper? Describe to me where this came from, the genesis of it, and its mission.
Sure. So Carbon Mapper is a nonprofit organization that we founded about 5 years ago in Pasadena with a public good mission to make methane and carbon dioxide data accessible and actionable. And we care about methane and carbon dioxide because they're the two chief global warming drivers. They're super pollutants that are driving warming of the planet and all the negative impacts that causes. And so our theory of change is if you can make the data visible and usable to a wide range of stakeholders, then they can take action to reduce those emissions. Excuse me, because these greenhouse gases are otherwise invisible. And the motivation for creating Carbon Mapper sprang out of over 2 decades of my work at NASA's Jet Propulsion Lab, where we worked on developing monitoring systems, global monitoring systems for greenhouse gases like carbon dioxide and methane, and a lot of lessons along the way, both technical and programmatic, regarding barriers to deploying those systems at scale.
Yeah. So how do you do it? How do you do it? I mean, we're talking about remote sensing. We're talking about sort of increasing, capabilities on orbit, whether it's just in terms of imaging, spectroscopy, or sort of even some of the data and the processing that kind of happens on orbit. But, you know, what's the approach here? Not only from sort of a technical perspective, but identifying where, because I imagine you have methane leaks all over the place, but some of these super emitters are sort of like maybe where you focus your targets a little bit more.
Right. So if you zoom out, and I'll apply my system engineering background here to look at kind of the end-to-end challenge,
Yeah.
is our theory of change is if the goal is to reduce methane emissions and carbon dioxide emissions, methane in particular, then you need to do three things. Number one is you have to be able to detect the majority of the high emission sources on the planet. We often call them super emitters.
Yeah.
So that's a question of completeness. How much can you observe with your monitoring system? And secondly is accessibility. Can you make the data available in formats that people can use in a timely fashion? And third,
Fast enough is, I think, is the question there too, right?
what's that?
If it's fast enough, right? If
Right.
there's huge latency with this data, then maybe it's not.
That's right. Speed is critical. It has to be within the interest horizon of people who can act on it. And thirdly is responsiveness. Can you create narratives and information out of that data that incentivizes people to use it and act on it? And that's a, a really complex and exciting topic given how diverse the sources of methane are on the planet. But in terms of how we do that first piece, the monitoring, is we use remote sensing developed at NASA over several decades that basically can detect methane and CO2 at the scale of an individual facility. And the way to think about it is like having a camera, except unlike a normal camera that sees in three colors, red, green, blue, like the human eye, our cameras actually see almost 500 colors. And those colors range from the visible wavelengths into the infrared. And it's the infrared wavelengths where we can detect invisible greenhouse gases.
Right. Getting buy-in at the corporate level, I think, would probably be sort of a hurdle in all this. And I was just sort of digging around, at least in terms of what you do. It's like it seems like part of the value prop for the corporate side of this is avoiding product loss. And like, I wonder how those conversations kind of manifest. Because if we're just purely talking about doing good in the world, the nature of like reducing methane emissions in terms of just the overall health of the planet, that is a very sort of nebulous kind of construct that you might go to a specific company with. Whereas if you're going to this with like, hey, you're losing product here, you need to sort this out. Walk me through that. Because I guess my question is like, it almost seems like you would need relationships with those companies directly.
Yeah, I mean, this is a fascinating topic, is the topic of incentives. Why act on the data to reduce emissions? And so there are several. You mentioned one, product loss. If you're an oil and gas company and you're producing natural gas as a product, then methane leaks are the equivalent of venting your profits into the atmosphere. That is product loss, right? And that's the easiest motivation to understand. But there are other motivations, for example, competitiveness in global markets, because there are jurisdictions around the planet. The European Union is one of them that is working to establish standards to reduce the intensity or the lossiness of natural gas supply chains. And so that's creating a differentiated market. Oil and gas producing countries that have dirtier natural gas, lossier natural gas, will be at a disadvantage to countries that can demonstrate that they have lower emissions. So that's a market-based incentive in addition to product loss. Other motivations include local health considerations. I mean, methane is usually not the only thing coming out of the ground, particularly with oil and gas operations. In some cases, there can be co-emitted toxics, and that can be often a very important health concern for local communities,
Yeah.
both governments and citizens, as well as the people operating the facilities who are being exposed to those potential toxics. So there are a range of motivations to tackle this, in addition to product loss.
I remember years ago, I was covering the oil and gas industry, and I was up in the Bakken region up in North Dakota. And I mean, first of all, I've never been that cold in my life. But second, in terms of some of these oil and gas operations, fracking operations, you'd see sort of these flares that would happen all across the landscape. And they were literally just, there's a byproduct of some of those operations. They were flaring off some of the natural gas. Now that's somewhat different, but it falls, I think, within the same category. And the argument at the time was that, like, just the investment in terms of the infrastructure wasn't quite there from a dollars and cents perspective to kind of address this. And so you just have this almost taste in the air as you're driving around, and you see these just flares light up the countryside. And I wonder, like, at that level, if a company is aware of this and still doing and still sort of venting, um, is that like it? It strikes me like this is where partnerships come in, and this is where working with sort of local and federal governments come in, because it strikes me like what you're doing is providing the data for addressing these problems, but there still has to be a wherewithal to address them in some capacity, right?
Yep.
So
Yeah, and that's the flare example is a really good one, because it highlights really two avenues for action. So the first one is that when oil and gas companies, and this also happens with landfills, right? When facility operators use flares, that is, they combust the methane to burn it off and convert it to CO2. Um, Many times there are assumptions that that is very efficient. In other words, the EPA standard numbers assume very high, complete in the high 90% combustion efficiencies, meaning most of the methane is converted to CO2. In practice, a lot of times those flares are pretty inefficient, and combustion efficiencies can be 90% or lower. And that's a lot of vented gas that could be avoided if you improve the efficiencies of a flare. So that's something that companies can address through investments. But we also find, and this goes back with our studies we've done with aircraft and satellites for almost a decade now, is that in many cases it's not an efficiency question, it's just the pilot light has gone out. So those
right.
are straight up malfunctions. And we actually find in many cases when we flag this for companies, they're unaware that the pilot light has gone out. I mean, it's literally just venting methane gas. And so there's some very low tech, low
Yeah.
cost things people can do to avoid things like that. And then to your point about partnerships, we actually find that where we have the biggest success rate with companies finding and fixing leaks is when we invest effort in reaching out directly to the companies or through local air regulators who have relationships with many of the operators.
Mm.
And what we find in those cases that roughly 50% of the cases that we report a methane emission, the operator reports that they didn't know about it and they're able to quickly fix it. And that's voluntary action. And so I call this the good neighbor approach. If you're a good neighbor, you let someone know when they've got an oil or gas, when they've got a gas leak or a water leak on their property. And the same thing applies here, is if you can let people know that they've got a methane event that they didn't know about, many times they'll take action voluntarily.
And there are real numbers behind this too. I remember, I think I saw something that there makes you represent like 3% reductions in terms of a state's overall sort of methane emissions, at least in terms of the bigger states. I mean, is that first of all, is that accurate in terms of what the numbers that I'm just quoting right now? But more importantly, like the cumulative effect of this, it's not just a sort of a piecemeal approach.
Right, the potential's there, and to be clear, if you zoom out and look at where methane emissions come from writ large on Earth, roughly half of methane emissions come from natural sources like wetlands and high latitude sources. The other half comes from human activity, and of that human activity, a lot of this. Uh, a- Actually, I lost my train of thought. Can you ask the question again? Sorry.
Yeah, no, no. I guess I'm trying to get a sense of like, you talk about individual companies, we talk about sort of individual oil and gas fields, and talk about like, different state approaches and local and federal regulators, but more in the sense of the cumulative effect of,
Yeah.
of what that looks like.
Yeah, so let me explain the term super emitter for a minute. It gets thrown around a lot. Scientific studies have shown now for some years, using surface-based measurements, aircraft, and satellites, that there tends to be a relatively small fraction of the equipment out there. And this is true for oil and gas, it's true for coal, it's true for landfills, it's even true for agriculture, where a small number of facilities are responsible for a disproportionate amount of emissions. So a typical number in, say, the state of California is less than 1% of the infrastructure is responsible for between a third and a half
Hmm.
of the total methane emissions in the state. And so we call the small fraction of large emitters
That's
super
remarkable.
emitters.
That's
It's, it's,
remarkable.
it's remarkable. Now, to be clear, this varies a lot by region.
Yeah.
And it has to do with, whether a region's methane emissions are dominated by oil and gas versus, say, landfills or, say, agriculture. And those numbers vary a lot. But what we've noticed over the years with our studies across different U.S. oil and gas and coal producing regions, as well as other parts of the world, is between 20 and 60% of the regional emissions come from these small number of super emitting facilities. And so what that means is there's a potential for really large reductions at a fairly small number of facilities if you can identify where they are quickly. That is the kind of the general theory of change around Carbon Mapper. And to be clear, this doesn't mean that this is the only thing that we need to do to tackle methane emissions. I mean, there's a need for a portfolio of responses, and that includes going after a lot of the small emissions everywhere through investments in the infrastructure and practices. But it also means doing this, go after the big leaks quickly, because we can have a fast impact that way.
Well, in that sense, also just the nature of, and I'm speculating here, so correct me if I'm wrong, but the nature of how you build constellation infrastructure, and I would imagine these are geosynchronous satellites that are focusing. Although I could be wrong on that, but it almost strikes me as that if you hone in on areas almost similar to the way the defense industry sort of looks at missile sites
Mhm.
in the security landscape, you might be looking at the super emitters in terms of oil and gas facilities. You don't necessarily need the thousands and thousands of satellites on orbit that it could be operating low Earth orbit. But I could be wrong here in terms of like your business model. But I wonder, because you've identified major problem areas and recurring major problem areas, having that focus specific to those areas might make your job a little bit easier.
Yeah, so actually, I can draw an example from the Weather Service to explain this, right? So, we've all become accustomed over the last several decades um, to have at our fingertips at a moment's notice detailed weather information. I mean, you can get on an app on your smartphone today radar images, satellite images, weather forecast, alerts. And it really is stunning the capability that's there that I think we often take for granted. And that's the result of decades of investments and billions of dollars in federal investments, government investments, and building constellations of weather satellites. Well, think about what those weather satellites do. They're a combination of satellites that provide continuous monitoring over the entire continent, as well as satellites that can provide higher resolution images. And the same is true for greenhouse gas monitoring. And that is what we're trying to do at Carbon Mapper as part of a broader ecosystem of observing systems. And just to clarify it, our own observing system, which involves the Tanager satellites that our commercial partner Planet is launching, are actually satellites in low Earth orbit. They're a constellation.
Yeah.
And that constellation, when we get enough of them in orbit, will be able to provide daily or more frequent monitoring, just like, some of the polar orbiting weather satellites. But additionally, there are other satellites, for example, operated by the European Space Agency or the Japanese Space Agency, that look at the whole planet and they provide more synoptic information at higher, at coarser resolution. So it's this system of systems approach. It's an ecosystem of satellites out there to which we contribute that really provide us with situational awareness, both at the fine scale, what's happening at individual facilities at 30-meter resolution, as well as the broader picture at continental scale. And that's, again, my analogy to the Weather Service, except this is more of a methane and carbon weather service.
Yeah, no, so low Earth orbit constellations certainly do factor in sort of maybe a more pronounced way than I was giving credit. But you mentioned Planet in terms of the partnerships and in terms of the constellations and like what you're looking at. I wonder if you can give us an update, like where that stands in terms of deployment of satellites and sort of existing partnerships and forward-looking notions of where you hope to be.
Yeah, so one of the more interesting things about this program we've built at Carbon Mapper is a public-private partnership that we started shortly after the nonprofit was created 5 years ago. And that partnership includes Planet Labs, our commercial partner, and NASA JPL. And the way this worked is that the instrument technology, this remote sensing technology that we're using, which was originally developed at NASA, at JPL. And so what Carbon Mapper did is we funded JPL to build the first instrument and transfer the know-how on how to replicate that instrument to Planet Labs.
Yeah.
So it's basically a technology transfer program. And then Planet is applying their agile aerospace model to building and operating many of these satellites, which they call Tanagers. So Planet successfully launched Tanager 1 about a year ago. We just had our 1 year anniversary last weekend, and it's operating beautifully. And they're on track to launch 3 more of these satellites as we speak.
Isn't that interesting though? So a lot of this R&D that happens at the government level, at sort of these high levels, things has a way of kind of trickling out into the commercial sector and have it be operationalized.
Actually, actually, my experience is that you use the right word, trickling out. And specifically this program, things were, I think, left to its own would have moved too slowly. And that is that the imaging spectrometer technology is something that NASA's been using on aircraft, but getting it into space has been a really long road. And so because we can't afford as a species to wait around on addressing climate change, Carbon Mapper stepped in with the support of our philanthropy donors to really accelerate this. And so it really was by, funding, specifically funding the technology transfer,
Mm.
was intended to really accelerate this. Because I feel like had we waited for this to more organically trickle out, we could still be waiting 10 years from now to make this happen.
Yeah, that's interesting. In the context of the technology itself, you talked about sort of the variety of different sort of colors and ultraviolet sensing and the nature of sort of all this new information that's coming on orbit, and then you sort of look at just like the nature of how to get this information back. And I imagine you're using, increasing amounts of machine learning and AI and how to sort of process this data. And I wonder if with this explosion of data, do you see bottlenecks that are starting to emerge in terms of these things? Or are you exploring sort of different approaches in terms of like how to get that information back? Because like all this capacity is great,
Mhm.
but you still got to get it down to earth in
Right.
a sense that makes it actionable, to use your words.
No, I actually think one of the things I'm proud of working with our partners in Planet and JPL is that all of the data is brought down. There's the infrastructure, the machinery, the satellites,
Mm.
the ground stations, the backhaul, the ground data systems, both at Planet and at Carbon Mapper, who collectively are responsible for the data pipeline, is very robust, and all of that data comes down. I think what you're poking at is where are the bottlenecks in getting the maximum utility out of the data. And the
Right,
thing
because
I would highlight,
you
yeah,
mentioned speed and latency is sort of part of that equation.
yeah. Well, I mean, again, on the latency front, we routinely now process data within 12 hours of it being collected. And we're able to actually, to notify subscribers within, less than 24 hours in many cases that we've detected methane, which is really important if you're trying to do this leak detection thing. But to your point about, about blockers, I think the opportunity and the challenge is getting the most out of this data because one of the theory of change things we did with Carbon Mapper and the Tanager satellites is create a system that's not just focused on methane and CO2, because that would be very much a one-trick pony, is that we deliberately
Mm.
picked a technology, it's called hyperspectral imaging, that covers everything from the visible into the shortwave infrared, literally hundreds of channels of information. And the number of applications of that data is not limitless, but it's a large number, probably in the hundreds of applications, not just methane and CO2. Things like agriculture, water quality, fire fuel loads, biodiversity, and mineralogy and so on. And so there's a huge, rich um, data set there that is yet to be fully mined by the universe of people who could use it. And so I think that's where advanced machine learning and deep learning and new algorithms are just starting to scratch the surface on this data set. I mean, Carbon Mapper's mining the heck out of it for methane and CO2, but there are many other applications that have not yet unfolded.
That's interesting. That's fascinating. I want to just take a little bit of a step back in terms of the nature of your story, your kind of journey throughout this whole process. Because I mean, you started Carbon Mapper, right? You obviously saw a need. Clearly, there is a need for these types of things, not only just in terms of the broader health of the planet, but how this responsiveness can help individual companies on a sort of a product loss and sort of a even just a sort of a human health perspective or crop growth perspective. But you spent a lot of your career, like I think it was 27 years at JPL, Jet Propulsion Laboratory there in Pasadena. And I wonder like what the difference is, like the cultural difference coming from near 3 decades at NASA and the institution and the heck of a reputation that shop has in terms of everything that's achieved. Mars landing notwithstanding. But what's it like now in terms of like pushing into this frontier of where you're calling the shots and you have maybe less, you may have less of that sort of institutional inertia that you have to contend with, but you don't necessarily have the same sort of support systems that might have been imbibed within age-old institutions. So I'm curious like how you're adapting to that and frankly what made you do it.
Well, I mean, this is a great question. It's in some ways, it's not as different as you might think, and that is, I do believe JPL is a truly special place. It is, objectively
That's fair.
a national gem in terms of its ability to innovate and do things that others dream of doing. What I learned at JPL was I don't know, a fearlessness to tackle things that are difficult and not to be afraid to quote break things. But there is a limit to that. And I think, to your point, when you're building the first of a kind, one of one in a universe type space mission, um, the risk posture has to be fairly conservative because the costs of failure are so high. And so if you think back to the early days of NASA, back when every other launch vehicle was exploding on the pad, the agency adopted a mindset of we're going to build two or three of everything because, we need to launch that many to get one successful. And over the years, as the launch vehicles became more reliable, the agency began to build bigger and bigger single missions, and that meant failure was not an option. That is part of NASA's mantra, and there are good reasons for it for in a lot of cases. But to your point, it does mean that there is some conservatism and risk averseness that is appropriate when you're just doing one. So
Yeah.
the big difference in what we're doing now as a nonprofit and working with our commercial partner Planet is basically a higher tolerance for risk. And part of that is because the way we've designed the program, we're not just launching one satellite, we're launching many. And so the risk is spread out. We don't put all of our eggs in one basket. And it also means we're working with funders, in this case, philanthropic donors, who also have a high risk tolerance. And if you think about where some of these people come from, their businesses and their backgrounds are in taking risks. And so that's the big difference is it is a different risk posture. I think it's appropriately higher risk. And of course, the reason why we take those risks is we need to move fast because the challenge we're trying to tackle doesn't allow us to move slow.
I think that's the interesting thing about this whole sort of new iteration, sort of this, commercial era, this space race 2.0, however you define like what we're in right now. It's been one of the hallmarks has been sort of this iterative approach in which failure is a likely option. And but there's also, a cultural shift that accompanies that makes that okay to some extent, provided, this is a big caveat here, provided we're not talking about human lives on the line, which I do think that changes. And, that's been less the purview of JPL and sort of more the sense of, Johnson Space Center and others, the questions about human operations up there. But in terms of like where you're taking this, I find this just terribly exciting, terribly important too. So thank you so much for joining us here on the pod. Riley Duren, Chief Executive Officer at Carbon Mapper. Thanks so much.
Thank you, David. It's a pleasure.